In the name of Almighty God, I am Master Sankoshi, and today I want to talk about piezoacoustic transducer. This type of transducer generates an electric voltage that is proportional to acceleration due to the pressure applied on a piezoelectric crystal. A piezoelectric accelerometer can accurately measure signals between 1 Hz and 15,000 Hz. These devices are well suited for taking high frequency vibration data, where large forces with relatively small displacement have to be detected. Some special transducers can measure much lower frequencies and also much higher frequencies. The collection of vibration data at high frequencies is conditioned by the attached method of the transducer to the machine. A piezoelectric velometer is constructed just like an accelerometer, but with a signal amplifier that performs an integration of the signal, since this stage of integration is down inside the velometer. The signal output is given directly in velocity units. The velometer takes advantage of the good frequency response characteristics of an accelerometer so that it generates a linear output over a much larger frequency range. That's the seismic velocity transducer. And what about the advantage of a piezoelectric transducer? Most sensors have a wide frequency range, usually between 2 Hz and 50,000 Hz. It should be noted that the frequency response is conditioned by the sensor mounting method in the machine. These transducers are very compact without moving parts, light and small, needing a small magnetic bases for temporarily mounting. An external signal conditioner is not required for the ICP, which means integrated circuit piezoelectric transducer type. Alto ICP is a registered trademark of PCB piezoelectronics, and it has become a generic term for an accelerometer with integrated amplifier. They are also often referred to more precisely as voltage mode accelerometer. Can be easily mounted with adhesive or screwed. Magnetic bases may also be available for temporary mounting or special applications. And what about the applications of the piezoelectric transducer? When used in handheld or a stinger mode to measure high frequencies, the signal response is very poor above 1200 Hz, and accelerometers need an external power supply. The amplitude output can be given in acceleration units. This output must be integrated to obtain the spectral representation of the overall velocity amplitude value. And the piezoelectric transducers and actuators concept. Piezoelectric ultrasonic transducers are available in a wide range of shapes like discs, plates, or tubes, and different performance levels. They can be adapted to application requirements by using different um, ceramics materials, electrodes, and assembling technology. They are present wherever ultrasound is needed, like in flu metering, structural monitoring, and many medical applications. Piezo actuators are available as stacked and multi-layer versions in different force classes and for displacements up to some 100 micrometers, while piezo bending actuators achieve up 2 millimeters. Their basic features are like millisecond response time and high dynamics combined with virtually unlimited resolution make them indispensable in applications from industrial production or dispensing to ultra precision positioning. And what is a transducer? A transducer is any device used to convert energy from one form to another. typically when converting input energy into output energy. For transduction to happen, a change from one form of energy must also take place, such as a conversion from mechanical to electrical energy or vice versa. There are many types of transducers, and the uses of transducers are widespread, impacting us in many ways. A common example is microphone, which converts the input energy or the sound waves produced by a voice or instrument to output energy or the electrical impulses in the form of amplified sound. And how does a transducer work? Transducers work through a conversion of energy and sound. Types of electroacoustic transducers include hydrophones, which converts changes in water pressure to an electrical output, and pickups on musical instruments such as guitars, which converts the vibration of the instrument's strings into an electrical impulse. And what are piezoelectric transducers? Piezoelectric transducers are a type of electroacoustic transducers that converts the electrical charge produced by some forms of solid materials into energy. The word piezoelectric literally means electricity caused by pressure. An early application of piezo transducer technology happened during the World War One, the First World War, with the use of sonar, which used echoes to detect the presence of enemy ships. Small piezo transducers were also mostly present in landline phones. They sat inside their ringer and helped to generate a noticeable noise to alert people to incoming calls. In addition, piezoelectricity finds a home inside quartz watches as well, which is what keeps them so precise. And what about the advantages and limitations of piezo transducers? As with all pieces of technology, carefully weighing a piezoelectric transducer's positives and negatives will go a long way in determining its effectiveness in a particular situation. Some advantages that they hold over other methods include: the first one is self-generating due to their material's ability to produce voltage while under the influence of some energy. Piezo transducers circuits don't require an external power source. And the next advantage is accessible. Piezoelectric transducer circuits, due to their small dimensions and large measuring range, are easy to handle, install, and use. And the next one is high frequency response. A much higher than normal frequency response means that the parameters of these transducers shift quickly. And the next one is flexibility. Due to how most of the materials used in construction can be shaped into different shapes and sizes, you can apply these transducers in various fields. As usual as they are, piezoelectric transducers also have their limitations, and that include some of the following. Sharp transducers now. Frequencies and amplitudes for piezo transducers. Oscillation of piezo elements starts when AC voltages are applied. Their incredibly fast response in the range of microseconds and lower allow them to be of use in wide range of applications, even including generating of ultrasound with frequencies all the way up 20 megahertz. Because of their extreme sensitivity to the piezoelectric effect, it's possible to create piezo transducers for applications ranging from sensors to ultrasound power generation. Doing so includes higher energy densities and frequencies ranging from 20 to 800 kilohertz. In this range of frequencies and amplitudes, piezo transducers that produce ultrasound energy are of excellent use in various medical and industrial processes. In the healthcare sector, these applications range from the removal of dental plaque to the ultrasound crushing of kidney stones. In industrial settings, piezoelectric transducers are ideal for use in various bonding, cleaning, and welding processes. Different modes of piezo transducers. Certain physical quantities, such as force and stress, are difficult to measure directly. In these instances, piezoelectric transducer output voltages are in direct proportion to any stresses and/or forces that are applied to the piezo material. Through the different modes of transducer measures, a scale can be set up to efficiently and accurately measure and apply force or stress. However, it should be noted that since the voltage output of materials undergoing the piezoelectric effect is relatively low with high impedance, piezotransducers often require some sort of amplifier or auxiliary circuitry to work effectively. And what about the transducer parts and functions? While many materials can show the piezoelectric effect, the best ones must also possess at least a few of the most desirable qualities. Such characteristics include consistent stability, high output, malleability, and resistance to extreme temperatures and humidity. That said, no known material exhibits all of those qualities simultaneously. Originally, crystals made from quartz took hold. Such characteristics include consistent stability, high output, malleability, and resistance to extreme temperatures and humidity. That said, no known material exhibits all of those qualities simultaneously. Originally, crystals made from quartz took hold as the primary material for piezoelectric crystal transducers. Quartz offers superior stability and slow measuring at varying parameters due to low leakage rates, which means it can provide excellent accuracy, hence why watches most often use them. While they are still in widespread use, quartz also yields a rather low output, meaning it cannot keep up adequately with demands of more sophisticated technology. In the early 1950s century, quartz crystals began to give way to piezoelectric ceramic as the primary transducer material. The advantages offered by a ceramic transducer when compared to other materials include ceramic's ability to be manufactured in a wide variety of shapes and sizes, its capability of operating efficiently at low voltage, and its ability to function at temperatures up to 300 degrees Celsius. Types of transducers. Due to the ability to produce ceramic transducers in numerous sizes and shapes, ceramic transducers can be easily adapted to a wide variety of industrial applications. Consequently, they allow for complete customization to meet a customer's specific needs. Today, the most commonly used ceramic transducer manufacturing materials are lead zirconate titanate compositions, a trend that traces its origin to the 1960s. As ceramic transducer technology has continued to evolve, the use of piezo polymers and composites has likewise gained acceptance. Another material that works incredibly well in transducers is Rochelle salt, which is a synthetic crystal. Of every medium that shows signs of the piezoelectric effect, Rochelle salt produces the highest output of any other material discovered thus far. However, it does have its drawbacks. which can hold back its success in certain environments. This synthetic crystal cannot come into contact with any moisture, nor can they be used at a temperature above 115 degrees Fahrenheit. If you are willing to trade off sensitivity for peak output, synthetic crystal can produce a distinct edge in performance over natural crystal. How to measure piezo transducer efficiency? One way to measure the efficiency of the transducer is to compare the amount of input energy versus output energy. Anytime energy conversion happens, some amount of energy will be lost during the process. In general, greater the amount of output energy produced in relation to input energy, the greater the level of efficiency that is present. The piezoelectric ultrasonic transducer generates ultrasonic activity, meaning it measures the pressure of sound waves above the frequencies that can be heard by the human ear. It functions by rapidly expanding and contracting when appropriate electrical frequency and voltage is applied. Typically used in cleaning systems, the expansion and contraction causes the ultrasonic cleaner transducer's diaphragm, which serves as the pressure sensing element of the unit to vibrate, introducing ultrasonic activity into the cleaning tank in the process. The piezoelectric ultrasound transducer also offers the advantage of high electroacoustic efficiency while minimizing heat generation. A piezoelectric transducer can be used either to transform an electric current to an acoustic pressure field or the opposite to produce an electric current from an acoustic field. These devices are generally useful for applications that require the generation of sound in air and liquids. Examples of such applications include phased arrays, microphones, ultrasound equipment, inkjet droplet actuator, drug discovery, sonar transducers, bioimaging, and acoustic biotherapeutics. These examples shows um, how to couple piezoelectric vibration in a transducer to an acoustic pressure wave in a fluid such as air or water. The physics that are coupled and solved are piezoelectric stress, strain, and electric field, and pressure acoustic in a fluid, and utilizing piezoacoustic sensors for the identification of surface roughness and textures. This study examines surface roughness measurements via piezoacoustic discs and appropriate signal processing. Surface roughness is one characteristic of surface texture that can have various irregularities inherent to manufacturing methods. The surface roughness parameters can corresponding surface profiles are acquired by a stylus profile meter. Simultaneously, elastic waves propagated along metal surfaces caused by the friction of a diamond tip are obtained in the form of raw sound via piezoacoustic discs. Frequency spectrum analysis showed apparent correlations between the traditionally obtained measurement parameters and the piezoacoustic measurement data. Thus, it is concluded that acoustic friction measurement shows promising results as a novel measurement method for the surface roughness states of certain materials. The surfaces of machine parts often contain irregularities that result from manufacturing methods. Surface roughness, one such irregularity, is one of the important parameters used to describe surface texture. Surface roughness can cause nonlinear problems in fluid systems, especially in motion parts that contact each other. Studies have shown that surface roughness affects contact pressure in interference fit, preload loss in bolted connections, surface wear properties, and surface coating properties. The fatigue strength of machine parts against dynamic stresses, the strength of adhesive bonded joints, and frictional losses in fluid systems. Surface roughness measurements is defined in ISO 2192 and has different parameters. Ra is the most commonly used parameter in determining the surface texture state, as it provides the most general and adequate information about the surface roughness. However, when the fluctuations are sudden and large in amplitude, the sensitivity decreases, and therefore it is a better option to use the other parameter where sensitivity becomes important, because the mathematical formulations depend on the five highest peaks and the five smallest valleys in the surface profile that they capture sudden spikes more accurately. In this study and simulation, the main goal is to establish a correlation between acoustic measurements and surface roughness measurements. Therefore, the comparison with RA in terms of the general condition of the surface roughness and the comparison with RZ in terms of sensitivity have to gain importance in terms of determining which parameter is more proportional to the acoustic measurement values. Therefore, both parameters are considered within the scope of this study. Surface roughness measurements are generally divided into contact and non-contact methods. A stylus profilometry contact measurement method is generally performed by moving a diamond tip over the surface. Non-contact methods generally comprise measurement methods that optically monitor the surface. However, in these methods, the surface to be measured must be exposed and accessible. Laser profilometry is a highly preferred non-contact method. In this method, the laser beam intensity is dependent on the material surface brightness. In this way, the surface roughness profile can be mapped. The roughness mapping process plays an important role in health and pharmacology sciences, where two-dimensional data acquisition is critical. In addition, modulography is a special case surface mapping method that is used for reconstructing Young's modules of coronary arteries from radial strain ultrasound images. Surface roughness studies remain one of the most interesting topics in mechanical engineering. In addition to traditional methods, new surface roughness measurement methods continue to be developed. These studies are also note how important it is to measure surface roughness values accurately, quickly, and effectively. Although acoustic wave sensors and technologies have been used in certain engineering system measurements, their use to define surface roughness has only recently attracted attention. Through the acquisition of acoustic or elastic wave propagation within solids, various physical data can be obtained and analyzed accordingly. Related studies can be seen in the literature as follows: the analysis of cutting parameters of machine tools with acoustic measurements, tool life prediction via sound frequency analysis, fault detection in roller bearings by wavelet packet transform in train bearing by improved harmonic product spectrum, and in low speed bearing using acoustic emission sensors. Plate fatigue evaluation using and high mode lamp waves. Investigation of the effects of elastic waves on fractures. And surface stress measurement with Rayleigh wave detection. In addition, while low cost allowed lead zirconate titanate transducers were previously used as buzzers for random sound generation. There are also studies where they are used as acoustic sensors for structural health monitoring. Moreover, PCT transducers and acoustic emission sensors are also used together to measure the surface quality in the grinding processes, and it was determined that the RE sensor and PZT transducer give similar responses to the stimuli from the grinding process. In a similar study in which RE sensors and PZT transducers were compared by applying the PLB pencil lead brake test on aluminum ceramic material, it was determined that the obtained frequency values showed that the PZT could be used as an alternative to OI sensors. In this study, the measurement and calculation of the RR and RZ surface roughness parameters are first investigated. Subsequently, the surface wave propagation equations are defined. The RR and RZ value of the prepared test specimen are then measured. Finally, all obtained data are transferred to a computer environment to be compared and analyzed. The piezo disc is connected to the computer through an IUX cable, and surface roughness profile graphics are digitalized. Using Audacity software, the piezo disc is detected as a microphone while the diamond tip of the Marmi M2 is moved on the specimen to measure the RR and RZ parameters. A sound recording was simultaneously initiated, and the friction sound of the diamond tip moving on the specimen was recorded. The main purpose here is to make the sound of friction and crackling, which are barely perceptible to human ear, into interpretable signals using the ability of piezo transducers to detect very low pitched signals or low amplitude vibrations at certain voltage values. The partometer M2 surface roughness measuring device performs the roughness measurement by moving the diamond tip forward and backward on the sample. While the forward motion speed is constant, the backward return speed can be adjusted in three stages. For the sound data to be evaluated accurately, the sound occurring at all operating speeds of the device is recorded and analyzed. The sampling frequency for all audio data is 44,100 Hz. Frequency spectrum data of each vector are created separately. Subsequently, the obtained surface roughness profile data, sound recording vector data, and voice recording spectrum data are all imported into the software. And what about the results? In the experiments, the RO and RZ parameters and the surface roughness profiles are obtained from the marked M2 device, while the original audio raw signal RRS, audio power spectrum OPS parameters, and power spectrum plots are created using the record sound data from the piezoacoustic sensor. Rs and ops parameters are calculated from the raw sound data and power spectrum data based on the RZ equation. An investigation of the roughness profiles for the aluminum specimen showed that there are no sudden fluctuations on the mild surface. However, on the ground surface, although the smoothness of the surface profile seemed to be preserved throughout the measurement length, sudden discontinuities were found in the two small regions. Accordingly, when a parameter comparison is made between the mild surface and the ground surface, the increase in mild surface values is found to be 5.53 times in the R parameter and the 2.56 times in the RZ parameter. Therefore, it is confirmed that a more sensitive value is obtained with the RZ parameter, and the results obtained in acoustic measurements accompanied with this parameter. The audio power spectrum of the aluminum specimen is provided here in this simulation. From this point on, for all audio recordings, the sampling frequency is 44,100 Hz. The local maximum values for this uh, specimen are observed between 800 Hz and 5,000 Hz. A legend abbreviation and corresponding sampling time values are provided in the results section. In the shortest sampling times are considered during the written stroke of the device tip. The frequency response is largely similar in form of for both the mild and ground surfaces, but the amplitudes are different. Additionally, it is determined that the amplitude values of the audio are inversely proportional to the length of the sampling time for all measurements. All investigation of roughness profiles for the stainless steel shows that no significant discontinuity is detected on either the mild or lateral surface. However, a small deviation and an increase in profile amplitude are observed from the 4 mm point on the mild surface. Thus, compared to the 3.459 times increase in RO values, 4.201 times increase in the value of RZ is determined. Therefore, it can be deduced that the sensitivity of the parameters doesn't create a serious issue for this type. The audio power spectrum of the stainless steel is provided here. The variation between the mild surface and lateral surface values appears as a shift in the frequency spectrum. The frequency response for the mild surface shows a two-step between 700 to 2000 Hz and 2000 Hz to 3200 Hz. For the latter surface, there are three steps between 700 to 1250 Hz and 1250 to 2000 Hz and 2000 Hz to 3200 Hz. The local maxima as the signal strength for the latter surfaces are between 700 to 1250 Hz, and investigation of roughness profile for the IISMI 1040 shows that considerable discontinuities are detected on both the mild surface and the ground surfaces in terms of surface quality. This situation creates a large variation between RO and RZ values, especially for the same machine operation. When considering these differences, it was determined that the RO parameter in particular doesn't provide sensitive values for this type. The audio power spectrum of the RISI 1040 is provided here. The frequency response for the ground surface spans a wide bandwidth and is observed between 700 to 1200 Hz, 1200 to 2000 Hz, and 2000 to 3000 Hz. The frequency response for the mild surface shows a unique amplitude spike, unlike other type at approximately 7,000 to 8,000 Hz. Piezoacoustic data obtained for all samples and production operations were evaluated in three stages: a parametric analysis, a power spectrum analysis, and finally a comparative analysis with standard parameters. The RMS and the R's acoustic surface roughness parameters obtained within the scope of the first stage provided accurate information, especially about the surface quality obtained with the different production methods of the same material. These parameters guided the other states by taking lower values on the smoother surface for all materials. Then sound power spectrum graphs including all sampling rates, materials, and production methods were produced. The power spectrum of the aluminum sample showed a frequency response compatible with the surface roughness profile obtained by standard measurements of the same material. In this graph, it is determined that the smoother surface creates a low intensity signal strength and the signal strength increases when the surface roughness increases. When stainless steel samples are examined, it is seen that the greatest difference between the lateral and mild surfaces is difference in frequency response. It is clear that this situation is due to the very tight formation of the yields and pits, especially on the lattice surface. Due to the aforementioned tide formation, the timbre and the frequency of the sound were increased in the sound recordings taken from the surface, this was determined as the frequency shift in the power spectrum graph. This result was shown in the power spectrum graph together with the roughness profile graphs, where the surface quality of the RISI 1040 material is problematic. Unlike other materials, the surface conditions showed sudden spikes even around 7,000 Hz. When considering all these results, it can be seen that an examination of the power-dependent power spectrum graphs will provide as much information as the profile obtained by the traditional method, including the information related to the maximum and minimum values of the peak and true values, as well as the frequency axis in the power spectrum graph. It has been observed that it can be obtained by working on it. The apps values obtained from the sound power data of the system also obtain a numerical value comparable with the RZ value among all materials depending on the correction parameters, the material density, and the surface speed, especially for the horizontal material on the horizontal axis. Whether compact comparison for stainless steel or irregular comparison for RISI 1040. A surface roughness value with high sensitivity, including spreading information, has been reached. Piezoacoustic versus optoacoustic sensors in laser processing. Piezoacoustic sensors are well known in the field of acoustic emission since the 20th centuries, but are considered as a common product since the 70s. Since that time, the number, type, shape, and temperature range of all sensors have been broadened to satisfy the industrial demands. When considering either high temperature and or a small size, piezoacoustic sensors have limits, and alternative technology has to be considered in industrial applications with special requirements to high temperature tolerance, small size less than 150 micrometer, broad frequency response in insensitive to electromagnetic interference. Optoacoustic sensors, including fiber Bragg grating or FBG, are very good candidates. Fiber Bragg grating is an interferometric structure imprinted inside the core of the optical fiber with unique spectral characteristic of reflectivity. The acoustic waves created during an industrial process result in periodic extensions compression of the optical fiber core and consequently the FPG structure. These momentary deformations affect the reflectivity properties of FPG that follow the behavior of the incoming pressure waves. This behavior results in the intensity of the reflected light that encodes the momentary deformation states of the fiber core, and so can be used for acoustic sensing. These sensors exhibit linear response in a broadband frequency range from the several Hz to 10 of megahertz, with potential detection upper limits of the order of several hundred megahertz. In contrast, most piezo sensors have linear response in a limited bandwidth and lower detectable frequencies. In the simulation, we will focus on the fiber technology and compare the sensitivity of commercial FPG with several piezoacoustic sensors. We will also show how FPGs can be used as acoustic sensors in laser processing by analyzing the data with the state-of-the-art machine learning techniques. In particular, for classification of laser power made from the sample itself, which can be related to its quality, this paper presents an investigation of using modified optical parameters, in particular fiber Bragg grating and phase shifted FPG or PS FPG as acoustic sensors. The sensitivity of FPG and PSFPG is also compared between several piezoacoustic sensors. To demonstrate the potential use of FPG industrial process, they have been tested in laser processing for determining the laser power from the sample itself, which can be related to the sample quality. Optical fiber based sensors have been the subject of research for more than 40 years. The research has been driven by the attractive properties of the optical fiber platform itself. It includes its small size, flexibility, immunity to electromagnetic interference, allows high temperature stability, high bandwidth, just to name a few. Among the large variety of optical fiber sensor technologies, the most researched and successful in both commercial and application terms has been the FPG. Fiber Bragg rating can be considered an optical band rejection filter or equivalent of a one-dimensional photonic crystal. Their function is a back reflection of a narrow wavelength band of light and the transmittance of all other wavelengths propagation in the fiber core. FPGs are formed inside the core of the optical fiber by periodically spatial modulation of the refractive index. The period of the structure determines the central wavelength to be back reflection according to the formulation where lambda b is the reflected wavelength, Bragg wavelength, and NF is the effective refractive index of the mode, related to the effective index of the propagating mode and affected by the magnitude of the induced refractive index change in the core. And lambda is the period of the refractive index modulation. Typically, such sensors are fabricated interferometrically by a laser-side illumination of the optical fiber through diffractive optical elements or phase mask that forms the periodic structure. A change in the periodic of the FPG results in the shift of the Bragg wavelength, providing the sensing capabilities of the FPGs. The detection principles of acoustic emission with optical fibers are based on two major techniques: optical fiber interferometers and FPGs. The first reports of interferometers-based optical fiber, i.e., sensors, date back to 1977. Ever since, numerous researchers have examined different varieties and implementation of those sensors. Despite their good sensitivity, optical fiber interferometers suffer from cross sensitivity as the whole fiber length that transmits the signal can be affected by external factors and alter the measure signal. Short length interferometers, for example, Fabry Perot cavities, overcome this cavity but lack dynamic range and require careful handling. While in the most cases lack any low-cost multiplexing capabilities, FPG for AE or acoustic electronic detection are a more recent advancement, first proposed in 1996 and have been extensively researched in the last years due to their attractive properties. The main ones are the small size, multiplexing capabilities, chemical and electromagnetic radiation neutrality, high temperature resistance up to 1200 degrees of centigrade for specific FPG. Also, the fact that the sensing element is sealed around the glass jacket, the optical fiber cladding makes FPG ideal for eye sensing in hostile environment. Besides the availability of numerous optical fiber components off the shelf at a relatively low cost is another significant benefit for practical applications. Recent research in the field has exhibited FPG-based setups with sensitivities up to 5 to 1 divided by 2 for frequencies larger than 100 kilohertz and detectable range up to the 10 megahertz. A performance which is similar or surpasses even inter interferometric setups. Moreover, the efforts to convert FPG sensitivity from omni to unidirectional bicylindrical housing were carried out with a large degrees of success. The utilization of the FPGs in RE detection is typically realized either by using the power or the edge filter detection method. The former is comprised of a broadband light source coupled to a circulator that interrogates one or more spectrally separated FPG. The back-reflected signal is routed to a demultiplexer that uses either a spectrally matched FPG or a narrow bandpass filter to extract the corresponding wavelength and supply the signal to a photodiode. This method is low-cost, highly scalable in terms of sensor number, and requires little maintenance, but at the cost of sensitivity. On the other hand, the edge filter detection method is significantly more sensitive and thus used when ultimate detection sensitivity is required. A typical setup is comprised of the components presented in this simulation: narrow line white tunable laser or TLS, optionally an isolator to protect the source from any light back reflections. A three-port circulator that feeds the FPG with light and routes the back-reflected signal to a photodetector. Alternatively, a balanced PD can be used where both transmitted and reflected signals are monitored. The working principle of the edge filter method is as follows: the TLS is set to a wavelength within the linear slope of the FPG spectrum. Depending on the spectral positioning of the TLS, a certain amount of light is back reflected from the FPG and fed into the PD, resulting in an output signal or IPD. An incoming acoustic wave will causes the FPG to vibrate, resulting in spectral blue and red shifts. As the TLS wavelength is fixed, this will lead to a change in amount of light back reflected and consequently a variation in the PD signal that is captured and recorded through an oscilloscope or a DRQ card. Graham and Hinckley have shown that the use of a second PD to monitor both transmission and reflection signals can enhance the sensitivity of the method by removing part of the direct current or DC noising originating from the laser intensity fluctuations. Alternatively, a balanced photodiode can be equally utilized. The sensitivity of the method can be expressed mathematically using the formula presented here. This feature significantly improves IE sensitivity, but at the cost of dynamic range reduction of detectable acoustic range. However, in the ultrasonic regime, the strength applied to the fiber is always small, and therefore the reduction of dynamic range is not posing a practical problem. In the work of the View and OCAP, they managed to achieve a frequency response above 1 MHz and a signal to noise ratio (SNR) of 28 decibel in the very near to 300 kHz frequency range using a PSFPG and balance PD. The minimum detected sensitivity of this system was estimated to be the order of minimum is equal to 9. In the present work, we demonstrate the use of FPGs and PSFPGs as RE sensors for laser processing. Actually, we will classify the laser power based on the RE signals acquired from the sample. That laser power can be related to sample quality. The signals from the fiber sensor were analyzed by wavelength composition and then classified by random decision forest. The efficiency of this approach was already reported in our previous work. The sensitivity of in-house produced fiber sensors was compared to the standard piezoelectric sensors. Experimental setup and industrial fiber coupled laser system star fiber 150 divided by 300p coherent Switzerland was used for welding. Details of the system can be found elsewhere. Single laser pulse experiments were performed on a 2 mm thick pellets titanium grade 5. The pulse duration were kept constant at 5 milliseconds. The laser powers were chosen to provoke different quality. The selected laser power were 20, 40, 80, and or 120 and 250 watts. After each pulse, the sample was moved by a distance of 0.4 mm to ensure a fresh surface for the following pulse. 35 pulses for each laser power condition were made, and the corresponding OI signals were used for training of the machine learning classifier. For the acoustic emission detection, a setup similar to the one and was used a tunable laser with 100 kHz line width was set at the slope of either a uniform top hat profile FPG or that a phase shifted FPG, both custom made in-house using the phase mask technique. At the laser exit, R is a greater than 40 decibel isolator was used to prevent light back reflection interference. In addition, a 1 to 2 coupler routed the signal to the sensing arm or FPG or PSFPG, and from there to photodiode or PD or balance PD. The optical fibers were glued on the bottom of the sample holder using the adhesive lactic, and this is illustrated here. At an equal distance from the weld point, a piezoelectric sensor PICO physical acoustic pack sensitive within the range 200 to 750 kHz was placed. It was fixed on the weld sample with a clamp to ensure good contact as shown here. The signals from the sensors were acquired with a Valen acquisition unit at a fixed sampling rate of 10 MHz. Wavelet sonograms were constructed from the acquired signals using wavelength decomposition with a Dulbecik motor wavelet with 10 vanishing moments. The obtained sonograms were fed to the machine learning framework to find the unique acoustic signatures for different power regimes. Among the 35 signals for which power 25 were used to train the algorithm and remaining 10 for tests. Experimental results to start with. The raw air signals obtained using the uniform top hat profile FPG are presented. In this case, a simple photodiode was used to acquire the data, thus no noise intensity filtering took place in the optoacoustic setup. Also here, the FPG raw signals are compared to the standard piezoelectric system for three different average well powers, which means 20 or 80 and 250 watts during a 5 millisecond laser pulse. In this first set of measurements, obviously the piezo eye sensors performs better with a clear ultrasonic signal detection, mostly in the 50 to 400 kHz range, while the unbalanced uniform FPG contains noisy data. The classification accuracy using the eye raw signals of the two sensors in the machine learning framework are presented here. In this table, the laser power related to the sample quality in RAWs versus the ground truths in columns are given. The classification accuracies in table are defined as the number of true positive divided by the total number of tests for each category. These values are given in the diagonal cell of the table. The classification errors are computed as the number of the true negative divided by the total number of the tests for each category. These corresponding values are filled in non-diagonal row cells. For example, for the piezoacoustic sensor, the laser power of the 120 watt was classified with an accuracy rate of 60%, and so it has the highest error rate for this sensor. The classification error is split between 80 and 250 watt, 10 and 20% respectively. Based on here the result, the classification accuracy favors the use of piezoelectric sensor. In this specific case, the underperformance of the FPG-based sensor setup has a threefold origin. First, the back reflection of the FPG is directly coupled to a signal photodiode, thus including the laser intensity and phase noise. These two sources of noise, especially in the laser intensity, account for a large DC component of the output voltage, increasing the signal-to-noise ratio, or SNR, by orders of magnitude. Second, the spectral profile of a typical uniform top hat profile FPG is not steep enough to adequate IE detection in the ultrasonic range, and therefore the use of a spectrally steeper FPG like a PS FPG would be required for a larger SNR. Finally, the mounting of the FPG to the metal sample holder can have an important effect on IE signal coupling to the fiber due to the significant acoustic impedance mismatch between the materials. It is important to mention that none of these factors were optimized in our experiments. In an attempt to overcome some of these limitations imposed by standard FPG, a 1.5 mm long phase-shifted FPG was produced in-house in a standard 125 micrometer optical fiber as well as in SM1500 optical fiber core LTD USA. The performance of the PSFVG was tested using the standard ASTM E976 test for the detection of a pencil lead break. The waveform acquired by a simple uniform FVG and the PSFVG is presented here. Calculation of the signal to noise ratio for the two FVG reveals an increase of 11 decibel for the case of the PS FVG detection as compared to the normal uniform FVG, which is in close agreement to the finding of Wu and Oka, where the gain in SNR was in order to 40 decibel. The result can be further optimized by using a balanced photodetector with equal widths on the both parts. That would require a PSFPG with at least a 50% reflectivity, which was not the case for our in-house made PSFPG. Using the PSFPG sensor with the current setup, acoustic frequencies of the up to 500 kHz were detected. Similar to the response of the Pico-Piezo sensor, a future work is directly towards the optimization of the sensing element itself, its mounting, and as well as setup improvement. Regarding to optimization of the sensing element, as the FPG are produced in-house, precisely engineered phase shift FPG are scheduled to be produced in both standard 125 micrometer and a smaller diameter such as 18 micrometer optical fibers. By doing so, the response of the sensor is expected to increase by improving the G factor in equation, as well as increasing the induced delta lambda b for the same actuation amplitude, which is caused by the smaller mass of the smaller diameter of the optical fiber. Concerning the mounting location, orientation, and placement of the optical fiber, several fiber orientation and orientations and placement methods, as well as holders designs, are under investigations. The performance of an airborne detection scheme fiber not attached directly to the IE pellet was recently tested, and the preliminary result shown here, they exhibit successful functionality with similar bandwidth as compared to a normal microphone. Finally, the use of 50 to 50 balance detection scheme on the setup is expected to improve the SNR by an additional 3 decibel, and low pass filters is to be used to exclude noise from ambient conditions, airflows, temperature, etc. Further enhancing the fiber functionality, conclusions in this simulation, standard piezoacoustic sensors were compared to several optical fiber-based. We could also conclude that the use of FPG-based RE detection system for laser processing applications in conjunction with machine learning algorithm for classification tasks has been demonstrated. The experiments showed that with a non-optimized setup, the uniform top hat profile FPG most basic system is more subjected to noise as compared to the piezo technology. Under these circumstances, the system in its most basic form, for example, unbalanced photo detection, and using a normal uniform FPG is underperforming compared to commercially available piezoelectric sensor despite its ability to detect the ultrasonic range. However, early, early results on the use of the phase-shifted FPG along with the balanced photo detection showed the very promising results. By improving also the mounting location, orientation, and placement of the optical fiber in conjunction with new holder designs, we expect that optoacoustic sensors either match and/or outperform traditional piezo-based IE systems with a smaller footprint, higher flexibility, and expandability package with next to zero maintenance needs. And here you can see that the simulation of piezoacoustic transducer with capsule software. As you can see, we have used lead zirconate titaniate for material, air, and brass, and the geometry here you can see that it's a quarter of a circle, and the physical module that I have used are based on pressure, acoustic, frequency domain, solid mechanics, electrostatic, and after that the combination of using of these physical modules can be acoustic structure, boundary, and piezoelectricity. And the sub physics and sub parameters here can be, for example, perfectly matched boundary, exterior field calculation, and for example, solid mechanics. You can see the initial value piezoelectric material that you can change here. I can see that the formulation that I have described while I was aforementioned to them, and you can see the parameters and minimum frequency of the study, maximum frequency of the study, steps in the frequency sweeps, speed of sound in air, thickness of the brass membranes, thickness of the piezoelectric material, radius of the brass membrane, radius of the piezoelectric material, and radius of the air domain, and deriving voltage, which is 5 volt. And the result can be acoustic pressure. You can see in the quarter of circle, we have this sort of acoustic pressure from this center that scatter and propagate forward and also backward to the environment and ambient. And the next one is second pressure level, acoustic pressure in three-dimensional, sound pressure level, exterior field sound pressure level, exterior field sound pressure level, and also the beam width, displacement, which is near to some millimeter. Mostly it concentrated at the center of this geometry, which is a quarter of circle, and the stress at the top of the membrane and pressure at the top of the membrane. The x-axis is based on millimeter and the radius coordinate, and the y-axis is based on the total acoustic pressure based on Pascal. And on axis second, the pressure level at 1 meter. And the x-axis is frequency based on kilohertz, and the y is on axis sound pressure level at 1 meter decibel. Thank you so much for watching my video until the end, and also you can download this simulation from github.com/masterscript.